Welcome to the 8th week of the live tutorial session for the point set topology course. So today we'll be mostly discuss problems related to countability and separability of a space. So these are the theory part of this week assignment problem. So we'll discuss some of them which are exactly related to the assignment question, and some are just conceptual question which will help you to understand the theory part. So first question is so that every metric space is first countable. So we didn't use this word first countable, but actually we did similar thing to prove some space is not metric space, because every metric space is first countable. So we'll also today also use this fact to claim that certain space is not certain topological space is not a metric space. So how to prove this one? What will be a countable neighborhood base for any point in a metric space? So suppose XDA is a metric space. Yes.
We can take open ball centered at any point X with rational radius.
Yes, exactly. So just the rational numbers are countable, so the collection will be countable collection, and just we need to show that that is indeed a neighborhood base around that point. That is again will be follow, because rational numbers are dense in the in whole real line, so in particular in the positive part of the real line. So the metric we are crucially using here, that's why the ball thing we have, so that so in general thing, general topological space, we didn't have this ball. So with respect to some matrix, so there we can't say the first countability, but matrix space we have this particular kind of open set, so those will serve as a neighborhood base around any point. So suppose is a metric space, and pick any arbitrary point x belongs to x. Then consider bx as all the balls dx r such that r belongs to positive rationals. Okay. Claim is this is a neighborhood base. dx is a, so it is countable as it is indexed by rational numbers, positive rational numbers, and rational number are countable, so this is countable. As q plus h, so is a neighborhood base. Okay, so proof is just take any neighborhood around this point x, or any open neighborhood u of x, there exists some, let's say, epsilon greater than 0, such that dx epsilon, this is contained in u, right? That is this is a neighborhood u, so that means a neighborhood of x, so x belongs to u and u is open, so there exists some ball around x which is totally contained inside u, right? Now I have to particularly say, so there exists some choice of this rational number such that bxr is also contained inside u, then we are done, right? So as q is dense in r, so there exists some, let's say r1 belongs to q such that 0 less than r1 less than epsilon. Okay, so 0 and epsilon two real numbers, in between them we'll definitely get a rational number, right? So then x belongs to bx r1, and this is purely as r1 less than epsilon, so this is a subset of bx epsilon, and this is contained inside u. So we get an element of this from, so this bx r1 belongs to bx, so that is for any one bd u of x, there exists bx r1 belongs to this collection bx such that x belongs to bx r1 contained inside u. So this implies bx is a neighborhood base. This ends so as x is an arbitrary point in the metric space, so this is first countable, so any point has a countable neighborhood base, so this is first countable. Okay, so the usefulness of this thing is basically in some cases, if you want to say that a given topological space is not metrizable, that means the topology does not comes from any metric, then you can just say that if you can prove that it is not first countable, then automatically this will imply that that cannot comes from any metric, because metric space are always first countable. So we'll use this thing in later problem. Okay, so let's go to the next one. I hope this is clear to everyone, pretty easy. Okay, so next we have that in a metric space, again in a metric space the separability of that metric space and second countability are equivalent. So in general topological space that is not the case. We have seen one example in the previous tutorial that the R uncountable set, so any uncountable set basically with uncountable set, so whose cardinality at least that of is R, so then that is with cofinite topology that is separable but not even first countable, so not second countable. So again the matrix space will somehow help to guarantee that separability is same as second countability. So one direction you don't need any matrix space thing, so second countable always will imply separability, but separability not always implies second countability. For that we need this matrix space thing. Okay, so how to proceed for the at least the not matrix space part? So basically this part, suppose X is a second countable space, let X be a second countable space. So this means that is um, so let's say B, which consists of elements Bn, n belongs to n, is a countable basis for the topology, basis of X. Okay, so now can you say what should be a countable dense subset in X, so that we can say that this X is separable? So for the separability we need a countable dense subset, right? So how to guarantee that countable dense subset from this information? Yes.
If we take points from each Bn
Yes.
for every n,
Okay.
but I don't know how that will be countable, but we have to also check it is dense, so which means its intersection with any open set
Yes.
in X is non-empty.
Yes.
That we guarantee, I think that we can guarantee, because this is a base, so for any open set we can get an element from the base which is
Yes.
contained in that set.
Right.
So
Exactly.
intersection can.
Yeah. Exactly. So correct. So consider this set. So like pick one element from each of these Bn. So take. So I'm assuming this like whichever this Bn is non-empty. So empty thing I'll just ignore them. I can ignore them. Even that is included in this thing, I can just ignore them. I just pick any from any non-empty Bn. I just pick one element from this. So take xn belongs to Bn for each n belongs to n such that Bn is non-empty. Basically, if empty, then I would not take anything from that thing. I cannot take, but that is even fine. But still, we have a choice of elements of this from Xn. So if I just then let's take then A equal to, let's say, xn such that n belongs to n is a countable set, obviously. Okay, countable subset of X, and claim is that this A will be dense. So H dense in X. That is again, I suggested, it's clear almost, because if to show the density I have to show that if I pick any open set in X, that should intersect this A. So pick any let U be any open set X, then I know this so this Bn, this B, which consists of this countable Bn, so they forms a basis. Then as Bj basis, okay, basis. So basis, so U equal to, actually I can write as union of some Bn, n belongs to some subset, let's say, again good notation, okay, let's say lambda, okay, for some subset lambda of the natural numbers, right? Now as for each bn non-empty bn, there exists xn belongs to bn, and that is also lies inside a. So u intersection a is also consist of all those xn, right? So this is actually union of, so basically xn, all the xn, so xn belongs to this for all n belongs to, right, a lambda with bn not equal to 5. Like b, obviously I should not consider, so okay, I should say this u is non-empty, otherwise this does not make sense of this family main. But anyway, whenever we consider this to check the like density, we surely consider some non-empty open set, right? So obviously some bn will be non-empty, so we definitely will have some xn in the intersection of u and a. This implies u intersection a is non-empty, so this implies a is dense. Hence we get a countable dense subset in our space, hence x is separable. So like kind of this second countability in any topological space is a like highest countability property. So if it a topological space is second countable, then you also know that is always first countable, because you just consider the all the open set in your countable basis which consist your that point which like around which you want a countable neighborhood basis. So first countable implies second countable implies first countable and also separability, but in particular matrix space, second separability also implies second countability. Okay, so in that sense second countability is the like kind of highest countability thing. Yes.
Sir.
Yes.
Sir, xn is a point in Vn. Is sequence of A is defined as a sequence of a point.
Yeah, just sequence of the points. Like kind of sequence, because I am picking one element from each of bn. So like bn, I'm like whichever bn is non-empty, I'm picking one element from them. And like as I already have numbered my bases like in terms of this n, so you may have numbering in terms of z or any like q, any countable set, but in particular all of them are like bijection with n countable. So so in particular I just numbered my this count basis elements as like by natural numbers. So that's why it looks like this the sequence, but like I could have numbered this in rational also, that is also possible, but all of them are like bijection with n, that's why it look like sequence. So you can also think of this is just a sequence. Okay, fine.
And sir, xn is in u intersection A for every n in the index set. So it is for some n or for every.
No, because just if you consider this u intersection A will be union of this bn intersection A, right? And xn or like this set, this xn is the precisely element in Bn intersection A, because that's why if Bn is non-empty, I choose my xn in Bn and consist A in that thing, right? So xn always belongs to Bn intersection A if Bn is non-empty by our choice of A. So yeah, and this is union of all those Bn intersection A. So U consist of all those xn where the n like Bn is non-empty, and in this particular lambda in the subset of this natural number. So all of them will lie there. So in particular, as U is non-empty, so one of the Bn is non-empty, hence we get xn. So at least one is there. So in particular, I say this is non-empty. That's enough to conclude that this is dense. Okay, so we get separability assuming second countability. So just to note that again, here we didn't use anything of the matrix space. It is true for any topological space. So for the converse, we'll use the matrix space part. Okay, so converse thing. So suppose XD is a separable matrix space. So separable matrix space means again we have a countable dense subset. Let A be a countable dense subset of X. Okay, so I have to produce some countable bases for this matrix space. So how to produce such thing? Any idea?
So, we can use that. We just proved that a matrix space is first countable.
Yes.
So for every element, we'll have a local countable base.
Yeah, sure.
So, and
But your X, yeah, X need not be countable. We have
yes,
instead of a subset which is dense. So yeah, almost like idea is almost correct, but you don't need all like this density will guarantee that you don't have to consider all those neighborhood bases, but you can consider only around the point of A, and that will guarantee somehow the basis because the denseness of A is there. So yeah, idea is correct. So we should consider all the neighborhood base around each point of A, and that will be a countable collection because already around any point of X I know there is a countable neighborhood basis, and I'm considering a countable union of countable collection, so that is again countable. So hence we have a countable collection. Then again remains to show that that is indeed form a base. Okay, so suggested consider B equal to union of A belongs to A and B A R all the balls around that point such that R belongs to positive rationals. Okay, so this is countable clearly. This is countable as okay, so this is A, countable as it is countable union of countable collection, union of countable sets right? And so claim is this is a basis, is a basis. So again I have to prove that if I pick any open set from this set X, then I have to like get some element from this collection B that is properly contained inside that thing, right? So for each element of the open set, so let U be any open set in X and X belongs to U. Okay, so again X is any arbitrary point. I will show that there exists a point in this collection B which contains X and contain inside U. Then that will say that this is basis, because I can take union over all those points X belongs to U, and that will provide me like U is union over all those elements of B, hence that is a basis, right? Basis means that any open set you can write as union of your taken collection, right? So that is enough to show that for each element you have a element from here which is contained inside U. Okay, so X belongs to U and U is open set in this metric space. So I have a again ball, some radius ball which is contained inside U. So there exists, let's say, okay, let me take R1. There will be many things. So R1 greater than 0 such that X belongs to Bx R1 contained inside U. And now like I have to fix two things, right? One is I have to take get a point from A and a rational number. So rational thing will not be a problem because I can always take something smaller if I get. So the main thing is to get this A from my dense subset, which like around which we get around which if I consider a rational ball, then that should consider consist of X. So like how to proceed for that, like how do you get an element from A using density? Any idea?
Because A is dense in X, so A has non-empty intersection with any open set.
Yes, sure.
In X.
Yes. Now like which open set you should consider in this case to get A?
Which open set? I need something from the base.
Something from the base, sure, but in this case like I'm saying which A like you should consider, like which open set you should consider which intersection with A is non-empty, and that will somehow produce
This
you
ball centered at X with radius R.
Okay, so as age dense Bx R1, this is an open ball in X, so this intersection A is not equal to phi. Okay, so just let me pick also the element as Y. Okay. Y belongs to this and this is not equal to phi. So there exists some thing from A. So now you have to somehow get some rational number, and like this Y belongs to A, so like I have to get some this B y some r2 which is contained inside bx r1, and that I know in constant inside u. So what should be a choice of r2? From this thing I know dxy, this is less than r1, right? So what should be your choice of r2? And obviously r2 belongs to positive rational. So what should be your choice of r2, so that guaranteed that this is inside this bx r1.
R2 has to be less than distance between x and y. So I can define R2 to be like half of the distance between x and y.
Half of the distance, will that surely, okay, let's take r2.
No.
So
Because it might be near the boundary.
yes, exactly. So you have to like take care of that thing. So y is somewhere here and x is in the center. I know this distance is r1, this is r1. So I have to get some rational thing you always can guarantee, but what should be your choice of the ball around y that is contained inside this bx r1? You should consider, you should measure this distance, right? So r1 minus the distance of x and y. So anything you just take r2 to be less than that. So basically then or 0 less than r2 less than this r1 minus the distance between x and y dxy. So 0 and r1 minus dxy both are like two not equal real numbers, so we always get some rational numbers in between them. So I pick that. Okay, then clearly this ball clearly contained inside this ball, right? Because if I take any, like it is almost clear from the picture, also you can just like algebraically also you can prove, as if z belongs to byr2, then by triangle just you have to use the triangle inequality, then dxz I have to say that this z belongs to bxr1, so I have to calculate the distance between x and z. So this is less equal to dxy plus dyz by triangle inequality, but dxy I know this is less than r1, and dyz yz is less than r2, right? Because z belongs to here, and r2 is less than r1 minus dxy, so this is did I miss anything? Dxy is less than, okay, I don't need this less than, okay, just keep dxy as it is, just have to put the r2 thing, okay, less than dxy plus dyz is less than r2, so this is less than r2, but r2 plus dxy is less than r1, so this is less than r1, so this implies z belongs to b xr1. So any z which belongs to byr2, that belongs to bxr1 also, so this is subset. So hence, and also obviously x belongs to here because dxy is less than r1 and like r2 is less than r1. because this is less than R1. So R2 is less than R1, so this thing is clearly there, so everything matches up, hence we have this thing. And so you just forget this B x R1, so you have some element y from A, so particularly this implies there exists B y R2 belongs to my collection B such that x belongs to B y R2 and that is contained inside U. This implies B is a base, right? For each element, so x is an arbitrary element in my open set. I showed that is contained in one of the element in my of my choice of open sets, and that is purely contained in U. So this is a base. Hence we get a countable basis, and that means it is second countable. Clear? Any doubt here? So this is R1 minus Tx1. Okay, so then let's go to the next problem. So here again, like how the countability and separability transform through a quotient map from one space to another. So suppose your f is a quotient map from x to y. So quotient map means again like any element in y, like f inverse u is open if and only if u is open. So f inverse u is open implies like u is open implies f inverse u is open. That part says that this is continuous map, but on the other part, this f inverse u is open implies u is open, that the like non-trivial part for this quotient map. So then like which of the followings satisfied for this particular kind of quotient map? So also quotient map means this f is surjective, right, or onto map. So it is continuous onto map and with some more information. So then can you say that if x is separable, then y is also separable or not? Any cases? So on the left hand side you have some countable dense subset. Can you get some countable dense subset on the right hand side also? Any idea or anything? Yes.
I think we can get
Yeah.
just by mapping that set.
Yeah, exactly. Just like that much only you have information, because if it is would have separable, then the only possible like choice of you have the possibly the image of that countable set. Yeah, so then you have to like only check that whether that is, obviously that will be countable, because image of a countable set will be countable, and like then only thing to check that is whether dense or not, right? So let's see whether that is dense or not for A. Let A be a countable dense subset in X. Okay. So then image of this set A is also countable. And now basically let's say claim F is dense in Y. So again, to check the density, consider an open set. It will be an open set in Y. We have to claim that U intersection F is non-empty, right? But again, to claim that thing, I have to somehow go to X and use the density of A there, right? But for any open set Y in U in Y, as this is quotient map, so in particular it is continuous, so this implies F inverse U is also open set Y, as if is quotient or in particular just continuous is enough. Now you have a sorry, this is in Y, then not Y, X, open in X. Now you have a open set in X, so this implies as A is dense, so F inverse U intersection A is non-empty as A is dense. And so you have a non-empty set on the left hand side, so you can just take the, like, I want to get back this U, but as F is surjective, so F of F inverse U, that will be U exactly, right? Is this clear why this F of F inverse U is U?
Yes.
Okay, so basically you are like, for each element of U there is a pre-image, so if you just consider that pre-image and F of that thing will be get mapped to there. So surjectivity is important here to claim that F of F inverse U is U. In general it will be a subset, but as F is surjective, so this is actually exactly U. So I can just take F of F inverse U intersection A, and that will be again not equal to phi, but F of this thing will be like F of, so individual applying F, so F of F inverse U intersection FA, so will that be exactly equal to this set F of F inverse U intersection A? So F of, basically F of, let's say, U intersection V, whether it will be exactly equal to FU intersection FV. Will that be true in this case, or any inclusion or something? Like, which set can be bigger at least? Yes.
This right hand side has to be bigger than the left hand side.
Yeah, exactly. So maybe U intersection, like for example, just consider X square. So you can take 2 and u equal to just consist of single point 2 and v equal to singleton minus 2. The image like intersection on the right hand side is just empty, but on the right hand side you have the intersection as 4. So basically this set is always bigger unless your map f is 1 1, you don't have the equality, but you always have the like inclusion of this set, this set. So as okay, so this is actually contains the set f of f inverse u intersection a, and this is not equal to phi again. So this in particular it contains a non-empty subset, so this set is also non-empty. So as this thing is there, and this again implies u intersection f a is not equal to phi because f of f inverse u is u itself to phi, as again this thing okay, f of f inverse u equals u. Okay, so we showed that we picked any arbitrary open set in Y and showed that intersect FA. So this implies FA is dense. So we started with a countable dense subset in X and get a countable dense subset in Y, hence X is separable implies Y is separable. So this is true. Okay, so what can you say about for the next part? Does first countable implies the second countable thing? So again I first would say that remark that here we didn't use the full information of the map F. The quotient thing we didn't use, only use the continuous and onto part, right? So, remark is that F is continuous onto is enough. So the continuity of F and ontoness is enough. Okay, so for the next part, can you say something? First countability or second countability? Does it will follow? Yes, no?
If capital X is first countable,
yes,
then from its local base, no, we cannot make a set.
Yeah, so
because X might be countable.
yes, so like again this thing here I consider the image of the countable countable dense set. So there you can also could not use the image of that countable neighborhood basis because the image F is not open. So there on the right hand side the set I will get that may not be open. So so image will definitely will not work there unless the map f is given to be open also. And even if it is given open, then you have to check whether that forms a neighborhood base on the right hand side or not. So like actually it will not true that if x is first countable and you have a quotient map from x to y, then y need not be first countable. So the example is basically, okay, so b is like should be false. So consider like a from r to the quotient r mod the natural numbers, okay, where this set is like consist of all the like r this mod n means. So this is by definition it is like consist of class of x such that x is related to x if like x only related to like this set is only consist of one equivalence, this equivalence class consists of only one element if x does not belongs to n, and x related to n or x belongs to natural number, like n comma x both belongs to natural numbers. So basically I am collapsing all the natural numbers in the set R to a single point, and in the other points remains as it is, okay. So this is a surely a quotient, like I'll give the I'll consider this x goes to class of x, and will give topology on the right hand side as the quotient topology induced by this f. That means a set here will be open if and if f inverse of that thing will be open. So by choice this is a quotient map, and R is second countable because like second countable or separable. Second countable because you can consider like open interval with rational endpoints, and that will give you a countable basis for R. And or we just have proved that in R is a like metric space with the usual distance metric. So there you Q have a separable dense subset. Like R is separable because Q is a countable dense subset in R. So from there you also can say that is second countable. So quotient and R is second countable. So in particular also first countable, and R is first countable as well as second countable. First,
Sir, can you explain this equivalence relation?
oh okay, so I'm saying that equivalence relation is basically if something x is not from the natural number set, then the only like equivalence class of that consists of single point. Otherwise all the like if and all the natural numbers are in one and in one equivalence class. So that's why I said that if x is related to only x, if x does not belongs to n, and x related to n for any n comma x belongs to like belongs to natural number set. So basically like is that clear or should I?
No, it's clear.
Okay,
Thank
okay,
you.
okay. So then the claim is basically this set R mod n is not first countable. Then that will definitely will imply also uh, that cannot be second countable, right? Because second countability implies first countability. So if I can show that R mod n is not first countable, then that will be not also second countable. So B is like C is basically not a separate part. If C is true, then A is also okay. That I should not say particularly. Like B can be true, but C may not true. But okay, anyway. So if B is not true, then definitely C will also not be true, right? So like if B is false, then C is also will be definitely false, right? So that's the like both are false. So claim is R mod n is not first countable. So can you think of some proof by contradiction or any direct means? So if you just see this thing like pictorially, kind of you can think of like this is it is ways of circle. So one direction you have a bunch like minus infinity to let's say 1, and then you have like all the others natural number points, you all like have collapsed them to 1 point. So it will like bunch of sphere bunch of circle all pinched to a one point. So like where should the first countability can fail? On this R mod n. Like there is definitely a special point, right, in this R mod n. What is that special point?
One.
Yeah, you can say that's this class of 1. So basically not first countable. So in particular, so that class of 1, let's say R mod n is not first countable countable at 1, which like consists of all of the natural numbers n. Okay, so suppose by contradiction like there exists some countable neighborhood base. If not, let un n belongs to n be a countable neighborhood base at 1. Okay, but so each of 1 belongs to un and un is open there. So now I will use the quotient part. So basically, so inverse of that thing will be again, so that 1 and then for each n belongs to n, f inverse of un is open in R. And what will be the like 1, the class of 1 belongs to un for each n, right? So the inverse image of that thing under this map will consist of all the natural number, right? And the whole natural number set is contained inside F inverse un, right? Because all of the natural number gets mapped to the class of 1 or class of 2, all of them are same. So the whole natural number set is definitely contained inside this F inverse un, and this is open in R. So for each natural number you will get a like some neighborhood around each of the natural number point, right? So this implies there exists epsilon m greater than 0 such that n minus epsilon m, obviously, okay, so I particularly considering for n, so I should give another also epsilon nm, okay, nm and n plus epsilon nm, and that is a neighborhood in of n inside R, right? So that should contain inside this F inverse un for each m belongs to the natural number, and also n belongs to the natural number, because I will also vary the uns. So now can you find an open neighborhood around this point 1 on the right hand side, which will not contain any of this un? Then I can say that I have a neighborhood of 1 on the right hand side, and there does not exist any un in my countable collection of open sets, which is contained inside my choice of open set. So this un cannot be a neighborhood base at 1. So can you think of some neighborhood around 1? Yes.
So any neighborhood around 1 with radius small enough will not contain.
Yeah, exactly. So I know this epsilon m is there inside there, so the content inside F inverse un. So if I pick for each, I can just fix this n equal to m, right? Then I will differ for each un, I will differ exactly at the nth position, I will differ this epsilon m, so that thing is less than this neighborhood, so that neighborhood will not contain this particular thing. So that also implies that none of the un can be contained inside my choice of neighborhood. So take okay, for each n belongs to n, take 0 less than take delta n greater than 0 such that delta n less than epsilon n in. Okay, I'm just particularly differing at the for un, I'm differing at the natural number n, the neighborhood around the natural number n. Okay, now consider f of these things. So unions of n belongs to n and n minus delta n plus delta n. So this is a neighborhood around n in the natural number set, so I'm taking union over all those things and taking image of that open set. on the right hand side. As this is union of open intervals or so open sets, so this is open, so f of that thing will be again open, right? Because exactly inverse image of that thing will be precisely this one which is open. So a open neighborhood of class of 1, right? Because it consists of all the natural numbers in this thing, so definitely class of 1 belongs here and also open. Then and then as okay, n minus delta n plus delta n, this is actually properly contained inside n minus epsilon n plus epsilon n for all n belongs to n. This implies that if I take the f on both sides, then f of this thing will be, this implies f of n minus delta n plus delta n, the whole image of this thing under f will be again contained inside f of n minus epsilon n plus epsilon n, and f of this thing again contained inside f of un, right? So for all n belongs to n, so this set, this open thing which is actually union of this f of n minus delta n plus delta n, that is actually all of them is properly contained inside f of un. So f of un cannot be contained inside this thing, right? So this is clearly a bigger set, this cannot be contained inside inside this set. So we can also further assume, like to guarantee that this set does not intersect each other, so I can in particular also consider like minimum of epsilon n and let's say 1 or half, maybe half, to guarantee that they are all disjoint union. This is basically disjoint union, right? Because it's less than half, so n minus delta n plus delta n, and if you take the next one, they will not definitely intersect each other. So this is disjoint union of those things. So this implies, let's say let me call this set as V. V equal to this thing, and this implies there does not exist any n belongs to n such that un is contained inside V, right? If it were some un that contain inside V, then f of un would contain inside this f of V, but f of V, I'm one part of that thing, I'm saying that is proper subset of f of un, so that cannot happen. So such that this implies this collection. So again let me take B as this. Yes, any comment?
Sir, I think B is not f of this thing, but B is actually this union of, like, B is not should be a subset of R.
No, v because I want to like get the contradiction on the R mod n, right? I'm considering the neighborhood base of this class of 1 on R mod n.
So can you please repeat this part, because after epsilon m prime it's not clear.
Okay, so I'm saying that like I want to get some contradiction that this like such countable neighborhood base cannot exist. So to show that I'm my idea is to get some open neighborhood around this one on in R mod n, uh, which is not like which cannot be expressed as union of the of my chosen collection of countable neighborhood base. So that will contradict that this cannot be a neighborhood base. So for that reason, how do I get such neighborhood? I'm saying that this, if I pull back each of un contains 1, so f inverse of un that is open in R and also contains the natural number set, because f inverse of that thing, f inverse of 1 will exactly n, whole of natural numbers. So n contain inside f inverse un, and so each of the natural number point is an interior point of f inverse un, and R you have the like this usual distance matrix. So I'm just, so there exists some ball epsilon nm ball around n, and that is okay. I should that I should consider m. Okay, yeah. So for each natural number m I will get some epsilon nm such that m minus this epsilon nm ball should contain inside f inverse un for each m belongs to n as well as n belongs to n, right? So that's why I took like epsilon nm depending on two things, one the n that comes from u and another for the natural number. Now you kind of give the diagonal argument to claim that some you have some neighborhood which cannot be contained which cannot contain any of the uns. So that will give me contradiction. So that's why I took
Sir,
yeah.
is it possible to define such a delta n?
Yeah, delta n I'm just taking the minimum, because epsilon nm is like some positive thing. I'm taking something
Sir,
lesser than that. Yeah.
So it's not the minimum of every epsilon n double prime. It's only the minimum of epsilon n double prime.
Yes. For each n you have a choice of epsilon n. Like I'm also fixing the m. I'm deferring my set only at the n position for the nth natural number for un. So that's why I took like lessing the only n. Yes.
When we already have epsilon n double prime.
No.
Taking delta n?
Okay, not this is okay. So that might be like confusion. This is n, not prime. Okay, that might be. So there is two dependency. That's why I this notation nm. Okay, like one dependency comes from my choice of this open this neighborhood base elements un, and another comes from the natural number, because m is a natural number and that is an interior point of this f inverse un. So
yes, sir. Okay.
So that's why you have like this epsilon nm choice. So once
So
for
now
this,
we are taking minimum of diagonal.
yes, exactly. So diagonal. So I'm varying like usual thing. You as you prove your like this open 0 1 is not countable by contradiction. You like consider all the enumeration 1 1 as something, then defer all the like points in the diagonally, and you get something which is an element inside 0 1 but not in your countable choice. So exactly the same argument here also I'm doing the same argument. So suppose it has some countable thing, and then I'm constructing a particular neighborhood differing each of f inverse un at nth natural number. So that's why I pick something lesser than that. So f inverse like un cannot contain inside there. Okay, so that's how I that's why this particular epsilon nn just differing at f inverse un at the nth natural number. And half I'm just to ensure that this is disjoint. You can take just less than that thing, but somehow that will be more easier if you take the disjoint union of this thing, because now delta n is less than half, so surely this will not intersect any other thing for each natural number. So this is disjoint union. So B is actually disjoint union of f of no, not disjoint union, but union of f of n minus delta n, f of n plus delta n. Now f of n plus delta n, n minus delta n, and n plus delta n, that is properly contained inside f of un, right? So this implies that there does not exist any n which such that un is properly contained inside V, because if it were some n, then that implies that f of un is contained inside f of V. But f of V is union of these things, and at the nth thing I know that is a proper subset of this f of un. So there are elements which does not belongs to does not belongs to f of V. So this cannot happen. So as this is an open neighborhood around 1, but there does not exist any un which contain inside V, so this implies that this choice of my B is not a neighborhood base. Not a neighborhood base at 1, and which is a contradiction, right? Which is a contradiction. Hence this R mod n is not first countable at the point this class of 1. Okay, that means it is not first countable, because first countable means it is first countable at every point. Okay, so the kind of related to assignment thing is, instead of quotient thing, if you have just open not exactly quotient quotient but per restricted quotient, if you have open continuous surjective map, then that is also a quotient map. We have seen that. So in that case, can you conclude at least B, or then if it is possible for C also, because if you have a neighborhood base, you can take the image of that thing around that point, because already you know for each point in Y there exists a pre-image. So you just consider at some neighborhood base at the pre-image, and they take the image of that under F. That will be surely a collection of neighborhoods around your chosen point on the in Y. So only thing you have to check whether that is still a neighborhood base or not. In this case we can't do such things because F is not open given. So if I take just the image, so if I just take the image, then that not necessarily be give me open set. So the somehow the open thing is somehow seems to be necessary to get the image to be open neighborhood base. Okay, so once B is not true, so C again is not true, because second countability implies also first countability, but not first countable implies not second countable. So again the same example will hold for C also. Okay, is this clear, or still any point, any confusion? Okay, so then let's go to the next problem. So here again, like as I said, that if you have open continuous surjective map, then if x is first countable, then y is also first countable. So again I'll just leave the first part. So basically idea is basically, if let y belongs to y, as f is surjective, there exists x belongs to x such that fx equal to y, as x is first countable, okay, countable, there exists a countable neighborhood base bx, let's say that is consist of elements bn such that n belongs to n around x. So the claim is that, so I'll not prove the claim. So claim is basically that f of bx, so that means all the f of bn such that n belongs to n is a countable neighborhood base at y. So clearly these are, as bn's are open, f is open, so f of bn is open. So okay, all of these are open owing the neighborhood base. Okay, and only thing you have to check that if you pick any open set around y, that should consist at least one of f of bn. Okay, so the just note that in the previous thing this f map is not a open map. Okay, so somehow that fails to give that R mod n is not first countable. So openness here is important. So like in general quotient map you don't have the image of first countable space is first countable, but if the quotient map comes from some open map, then it is indeed. And can you guess something about the converse, whether if you have a continuous open surjective map, then y is first countable, does that imply x is first countable? Okay, any guesses about the converse? Okay, so the converse is actually will not be true. Again, converse is not true. Example, you can take like any first countable non-first countable space x as any non-countable space, and on the other hand y you can take like a single point and consider the constant map. Then the constant map definitely is continuous, open as well as surjective, but on the right hand side you have first countable space because the whole topology consists of only 2 points, and on the other hand x is not first countable by choice. So take just x is one such example you also have seen. So takes x equal to r with cofinite topology. And y is some single point. And if x to y constant map. Then clearly y is first countable or all countable, second countable, separable, all of this thing. First countable, but x is not. Fine, so converse is not true again. Okay, so let's go to the next one. So here like kind of like productivity property of the like metric space, if you consider the uncountable product of metric spaces, so in the product topology that will not comes from any metric. Again, as I said, so to show that in this case, to show that this is not metrizable, I'll show that this is not first countable. Like product of uncountable, so the thing is basically each of them are matrix spaces, so each of them are first countable, but uncountable product of those things. So to avoid the triviality, I must consider the matrix space with at least 2 points. So in the topology I at least have two like non-trivial open set, right? So again will show product space, let's say x, which is product of this uncountable product of this xi uncountable is not first countable. For this xi di matrix spaces. So like you already have seen some theorem about the like product of first countable space is when first countable. So from there, can you say why this is not first countable? Can someone recall what was the condition? So there is a condition that product of some arbitrary collection of set when it is first countable. because each of the xi di are metric spaces and first countable, so when the product of them are again first countable. Someone recall what was the condition? Okay, so let me recall the condition that here. Okay, just let me no, this x is first countable if and only if one is each xi is first countable and second is if you consider the set let's say I sigma, let's say, okay, or gamma. Okay, consider the gamma as a subset of this index set lambda as all this I belongs to lambda such that xi has a Sierpinski point. I'm missing. So is this has a Sierpinski point or not? So this is okay. So has no Sierpinski. Has no Sierpinski point. So can someone recall what is this thing, Sierpinski point? Which point calls in a space Sierpinski point? Yes?
So, if in a topological space, if there is a point for which the only open, non-trivial open set which contain that point is the entire space.
Yes, exactly. So, so if this set, so this is a subset of lambda, is countable. Yes. So then if these two conditions are satisfied, then only x can be countable. So here the first condition is satisfied because each of xi is a matrix space, so hence each of the xi are first countable. But what about the second condition? Is this countable? Gamma in this case? What can you say about gamma? Each of xi is a metric space with at least 2 points. So can there be some like Sierpinski point in a metric space?
No.
Yeah, exactly. So because it has 2 points, if it were the matrix space consists of only 1 point, then that point will surely be a Sierpinski point, right? But it has 2 points, so you definitely have neighborhood around each of those things, so they are non-trivial open set in that set. So as xi as each xi is a metric space with at least 2 points. So it does not have any here Pinsky point for all I belongs to this, the indexing set. This implies the lambda set. This is all of this gamma set is all of lambda, and lambda is uncountable. So thus this x cannot be first countable. So if you don't want to use this particular theorem, so then you can try directly try to prove by contradiction that this is cannot be first countable. Again, like similar kind of not kind of diagonal, but prove by contradiction that there cannot exist a for each point, you don't have to pick a particular point, you pick any point, that point will at that point the x will not be first countable. Okay, like similar kind of idea as we did in the last thing to get such neighborhood. Okay, so that means that in the product topology of obtained from uncountable product of matrix spaces, that is not metriizable, right? Okay, so let's go to the next one. So here is like a bunch of this thing, like in matrix space we already have seen something like second countability and separability are same, and so but they are like all of them are something. So basically I already know second countable implies first countable and in any general topological space, and separability okay, so that is different thing. So second countability also implies separability. So okay, that thing is a part of this thing. So okay, so can you give me some example, or whether it is not possible that first countable but neither second countable or separable? Any example? Anyone? Like there is no restriction in like metric space. It can happen that something is first countable but neither second countable nor separable, right? So anyone have any example which is first countable but not second countable or separable? Like think of the basic the most easy discrete metric space. Is that first countable discrete metric space?
Yes, sir.
Yeah, exactly. So you can just take the single point as neighborhood base. So but discrete metric space will not be second countable if you consider the discrete metric on an uncountable set, right? Because then you can consider like you cannot have a countable neighborhood basis, because all of the singleton points are open there, so you have to include each of the individual open set, singleton open set in your base. That is the only possible choice of your base, has to contain the singleton set in your base. So, and if your starting state is set is uncountable, then that cannot be second countable, right? Similarly, separability is again the same thing, because in metric space separability can only second countability, right? So if it is not second countable, then also not separable also. So consider R with discrete metric. For any x belongs to R, the singleton x is a NBD base at x. So R is first countable, but as x is open for x belongs to R, so any base of R must contain the singleton x, right? Because anything, if I pick this as my open set, so the only set that is contained, like non-trivial set that is contained inside this thing is the singleton x itself. So it must have to contain all the singleton points, contain singleton x for all x belongs to R. This implies any base is uncountable, because it at least has to have R many open set. That is not second countable, and hence not separable. As we are in matrix space, okay. So B, separable but not first countable. Yes. Yeah, any confusion here?
The singleton set X is a countable neighborhood. Why it is countable?
No. Like which one? This for any x belongs to this is like consist of only one point, one element. Are you saying about this one or which one?
The set is
So for each x belongs to R, I am considering my neighborhood base as single, consist of only open set singleton x. That is an open set. and if I like, this is a neighborhood base because if I pick any neighborhood around x, that must contain x. So I can say always x belongs to this singleton x, and which is contained inside my open set. So this is definitely a neighborhood base at x. And for the second thing, I'm saying that if you have a like each singleton set is an open set. So for the base thing I need for each open set, there should some element from in my base which contain inside my open set, right? But singleton set, that is like only non-trivial set that it contains is the set itself. So my basis definitely will contain the singleton x for each x belongs to R. So the base consists of at least R many open set, and R is uncountable, hence this any base is basically uncountable. Like, is this clear, or I didn't get exact like where is the problem?
It is clear.
Okay, so like now separable but not first countable. Can someone think of some example? So something is like dense, countable dense, but not first countable. That means like the like only thing like we have discussed many times that which space is first countable, not first countable.
Sir, R with cofinite.
Yeah, so R with cofinite topology is not first countable. So does that have a countable dense subset? So Q is definitely a countable set. So whether Q is dense in cofinite topology in R.
Yes, because any open set there will contain almost all the elements except some finite number of elements.
Exactly.
So every open set will intersect with Q.
Yeah, exactly. So Q or any infinite set is dense inside cofinite topology, right? Because the only like finitely many elements, any open set will not intersect at most finitely many elements. So it will definitely intersect all the any infinite set. So in particular, you can take A and Z; they are also countable and they are also dense. So basically, R with cofinite topology. G is not first countable. We again have seen in previous thing. So not also second countable. But any infinite set is dense. So in particular, Q is a countable dense subset. That is R is separable. Okay, so I'm not mentioning each time the topology. So here R, when I'm discussing all the things with respect to descript topology, here this R is separable means R with cofinite topology. So, okay, so for the C part, separable and first countable but not second countable. Is it possible, or it is not possible? Every separable first countable is second countable or something? Okay, see, so I want to get some separable as well as first countable but not second countable, right? So can you think of at least some topological space which is not second countable but first countable? Okay, so this is basically, if you consider R with lower limit topology, that means the topology generated by the base, all the like hub open A comma B, left closed right open, A less than B belongs to R. A belongs to R. Okay, so can you see what is the countable dense subset here? Yes.
Same Q.
Yeah, exactly. The same Q will again be so, because Q will intersect every basic open set. So if you pick any basic open set of the form A closed A open B, that will definitely there are infinitely many rational numbers, so that will intersect Q. So we have again seen that to check, instead of checking for any open set, if you can check for the basic open set, if it is non-empty, then also it is still dense. So instead of that thing, so it is clearly follows from that thing that Q is dense in R as Q intersection AB not equal to phi for all AB belongs to R with A less than B. So this is a that is R is separable. So why this will be first countable? So for x belongs to R, what should I take as my neighborhood base? What should be my choice?
So I think same x minus R to x plus R. Closure it.
X minus R, x plus R.
R is rational.
Okay, so x minus r, x plus r. This is closed, this is open, r belongs to q. Yeah, sure, this will yeah, this will, no, will this be, no, this will not a neighborhood base, right? Because I can take x comma some x plus 1. It does not contains any set of this form, right? So this will not work in this case. Because that was in particular case of metric space, but this lower limit topology is not a metric space. First of all, I'm giving counter example where like separable but not second countable. So if it were some metric space, then separability and second countability are same there, right? So this will not be the choice of my neighborhood base, but you can consider this, right? Instead of x minus r, x plus r, you can just take x comma r, closed, open, and r belongs to q, r greater than x. Then this is also countable, because on the right I am only varying over q. So let's take b. Then b is countable, and also neighborhood, because if I let's say this is already a base, so if I take any open set inside this topology that contains x, so I definitely will have some x comma y, closed x, open y, such that x comma y contain inside that set, because this is like particular base. So from there I can take some rational number which is less than that y, and that will give me that this is indeed a base. And neighborhood base of x and r. So this I am again not wholly writing the whole thing, so but easy to check, just follows from the base thing. Okay, check. Is this clear or any confusion? You get why the previous choice will not work, x minus that r, x plus r?
Yes, sir. Yes.
Okay, so now the claim is this is not second countable. So can you see why it is not second countable? Okay, so again by contradiction, if r is second countable, then there exists a count, so then there exists b equal to, again let's say bn, n belongs to n, is a countable okay, not neighborhood, sorry, countable basis. Now for each x, now for each x, let's say x less than y, xy belongs to R, there exists some bn, let's say bnx and bny, such that bnx is contained inside x comma x plus 1 and bny is contained inside y comma y plus 1, right? Because x comma x plus 1 is an open set here, x belongs to there, so there exists some bnx in this choice of countable basis. There exists some bnx and here bny for y. Now this bnx and bny definitely will not equal, right? Clearly bnx not equal to bny, right? As x less than y and like this start with y, so x does not belongs to bny, as x belongs to bnx but x does not belongs to bny, because it start with, so everything whichever point lies in bny, that is greater or equal to y, and x is strictly less than y, so x cannot lie there. So for each x you can consider all the like real numbers which is greater than that, and for each of them you will definitely get a different bnx from your choice of basis, right? So thus x going to this nx is an injective map from R to this n, right? Is it possible there exists an injective map from R to n? Yes, no? So if you have an injective map from R to n, then what happens? Yes.
Sir, n is countable and r is uncountable.
Yeah,
There
exactly.
does not exist.
Yes, if there exists some injective map from R to n, then that means that R is countable, which is not possible. R is uncountable, so which is impossible. Possible as R is uncountable. So this is a like we arrive at a contradiction because we start with some countable basis here. So thus R can't have a countable basis. That means it is not second countable. So we got a topological space which is first countable and separable but not second countable. So the last part is basically this is second countable. So does there exist any second countable space which is not separable? So this is again we already have done in previous thing, that metric space you don't need, but in any topological space second countability always implies the separability. So there does not exist any second countable space which is not separable. Okay, so D is not possible. Okay, so I have few more things, so I'll just quickly go over them. So detailed thing I will write and upload in the drive, so you can check there. So if in a matrix space, actually Lindelof thing, if the matrix space is Lindelof, then it is also second countable, and second countable will again always implies the Lindelof thing. So the metric space part, the Lindelof thing will imply the second countability, but in general it will not hold that Lindelof is second countable. But second countable in any topological space is Lindelof. So if you have a countable choice of basis, then for a given any cover you can consider its subcover as those points which contains some of this countable choice of the basis. So idea is basically that, and in general thing it is not hold. So can someone think of some example where the Lindelof does not imply second countability? So compact space, again I will remind that Lindelof means any open cover has a countable subcover. So if your space is itself compact, then any open cover has finite subcover, so it is definitely Lindelof. So can you think of some compact space which is not second countable? You have seen, like, that is a example which produced most of the counter examples. Like R is compact in which like non-trivial topology, I would say, because in discrete topology is like there is only one open set, so that is surely compact. But other than in discrete, what else topology have you seen where the R becomes compact?
So R as a set compact.
No, R is not set. Like in which topology I am saying R becomes compact?
In discrete topology.
Yeah, indiscrete topology is there, but other than indiscrete topology, because in discrete topology it will be also second countable.
The co-finite topology, there also.
Yeah,
It
exactly.
will be
Yeah.
compact.
In the cofinite topology, you know already that is not first countable, so that is not also second countable, but that is compact, so it is Lindelof also. Yeah. So Lindelof just means the countable, but finite thing already means it is countable. So okay, so in general this is not true. Example is again R with cofinite topology. And for the Lindelof implies second countable, that is basically you consider for each n this collection of Bn, which is ball around each point of radius 1/n such that x belongs to R. So for each n, n belongs to n, you have a cover for your metric space, sorry, not x, the space which you are considering x. Then clearly Bn is a cover for your topological space x, because you are considering all the balls around each point of radius 1 by n. So this is definitely a cover. So by Lindelof thing, I know this has countable subcover. So let's say Bn prime is a countable subcover for this cover. So you take the union over all those countable cover, and claim is that if you consider B as this set, union of all those countable subcover of some countable subcover, and then take the union. So then it is countable union of countable sets, so again countable. So claim is that this is a basis. So this is again will like similarly will as we proved previously.
Sir,
Yes.
so Bn itself is countable. So why we are taking Bn prime?
No. Bn, why Bn is countable?
Because this 1 by n,
No, 1 by
n is fixed, x is
yes.
x varies. Okay.
So x, I'm around each point I'm considering 1 over n radius ball. So that's why Lindelof thing will imply that this Bn prime is countable. And from there actually you get this countable collection of sets, open sets. Now claim that this is a basis. Okay, so basically idea is that, and converse is already saying that if you have a countable set, let's say this is countable converse part, so this is a countable basis. Then you, and let's say U is any cover, okay, this is a cover for x. Then you consider as a subcover as, let's say, U tilde, as all those ui belongs to U, such that, okay, I should consider in the other way. So peak un belongs to U such that sorry, okay, for each, I should start for each Bn, peak 1 un belongs to U such that un contains Bn. Okay, if there does not exist for a like particular choice of Bn, there might not be some U inside un inside U which properly contain or just contain Bn. So then just drop that thing and continue whole process for each of these things. So as it already for each n, I'm actually picking one element from U, so this is by choice is a countable collection. So the next thing will be that is cover. So that's the only part. So that will be cover because again this is a basis, right? So for each open thing you have a element from your basis that is contained inside that. So definitely that will be a cover for your x. So then U tilde which consists of this un is a subcover, countable subcover. Cover. So again, to prove this one, we didn't use anything of the matrix space thing. So the only, if it is true for any topological space, that if it is second countable, then it is already Lindelof. Okay, so in that sense, like second countability again is the most list, all possible countability is included there. Lindelof is included there, fast countability, separability, all are included in second countable space. Okay, so I'll leave this to you, and I'll write part of this thing. Okay. Next, like in a separable topological space, if you have a disjoint collection of open set, then that will always be countable, because for each open set you can open set there exists a point from your countable dense subset. So you can actually map from a countable set to each of these disjoint open sets. So as your initial point is countable, so you have actually kind of the disjointness will give you a injective map from this collection of open set to your countable dense subset. So that means this collection is also countable. So that is very easy. And last one is basically, if you have a uncountable subset in a second countable space, then this A has uncountably many limit points. So this is again like if A prime denotes the set of limit points of A, then you show that this set is countable. So how do you show this is countable? So if some point in A is not a limit point of that set, then you will get some neighborhood around that point which intersect A at only single point, right? So if x belongs to x, this implies there exists some Bnx, and this Bnx comes from your countable basis, such that Bnx intersect with A is singleton only x, because it is not a limit point. So there will definitely will exist some basic open set which intersect only at this point. Now you consider this x going to nx, this map. This will again be an injective, and nx being a subset of natural number, like this is a map from a minus a prime to n. So this is an injective map, hence again this is countable, and a you can write as a minus a prime union with a intersection a prime, right? Now this is countable and a is uncountable, so this has to have uncountable. So so a intersection a prime is contained inside a prime, and this set is uncountable, that means a prime is also uncountable. So the a has uncountably many limit points, right? So that's all I have to discuss. Any confusion at any point, then I can just repeat once. Okay, then I'll stop here and we'll meet again next week.
Thank you, sir.